Buongiorno.
Good morning and welcome to these lessons dedicated to energy.
Il mio nome è Romano Borchiellini.
My name is Romano Borchiellini and I teach industrial technical physics. And what is this subject? Well, it is the science that tries to transfer some of physics knowledge to engineering. In particular, one of the tools that we often use in our analyses is thermodynamics. That is the tool allowing us to analyze those components, those systems and plants where energy is transformed. At the Politecnico di Torino, I teach applied thermodynamics and heat transmission, as well as the course in numerical design of thermal systems. I am also the coordinator of the Energy Center of the Politecnico. It's an initiative promoted by Politecnico to study the energy transition with a multidisciplinary approach. And what do I mean by this? Well, the center has several professionals who have different backgrounds, including engineering, architecture, economics, and social sciences. So we're trying to interpret this issue of energy transition through the contributions and perspectives of different professionals. You will have attended Professor Pievani's lessons, who explained the wide and complex scenario of global challenges. Now, my task is to introduce you to a subject that is just as complex. So, energy and energy transition. And the aim of these hours is to help you perceive how complex and wide this issue is, and try to help you to look at these problems with more attention and maybe a more critical approach than the approach you've always used when receiving information through the media. And also to provide you with some more tools to attend the courses that will follow. I decided to start with these images to highlight the fact that the term energy makes us think of very different situations and different meanings. We use or we associate the term energy to great natural events like a volcano erupting or lightning striking or a bushfire. Or, as you can see, we link the term energy to sea waves, but not just to the sea. We also link the term energy to the act of that athlete surfing on the waves. At times, we use energy as linked to emotional states, like expressing one's happiness with energy, or to acts linked to our mind or thoughts. So you have a lot of ideas, you're full of energy. And lately, we have been using the term renewable energies. Our muscles also bring us back to the term energy. And then I also included this image with electricity cables, because oftentimes the term energy is used as a synonym of electrical energy. And then our body needs energy. Often we hear athletes, or even we ourselves, we say that we need to recharge our batteries, we need energy. So food is also linked to energy. And talking about energy in just 3 hours is quite challenging. And therefore, it is a challenge within the challenge, because we're within the scope of global challenges. And I will have to try and give you a framework or an overview of all the issues linked to energy. And this is quite challenging in such little time, because energy is always included in our actions and in everything that surrounds us. So the argument can become very wide and very general. So let me underline again that these hours will not be an exhaustive analysis of all the aspects and phenomena and products that can be associated with the term energy. But I will focus on the meaning of the term energy in the scientific and technical fields. I will try and give some interpretation tools and food for thought that I hope can help you to better interpret everyday life messages and also the messages of future courses. So to conclude this brief introduction, I would like to highlight the fact that the phenomena surrounding us, as I was saying, they are associated with very different quantities of energy. That is, we have a very wide range of energy values associated with the various phenomena surrounding us. Here, you can see that we go from joules, which is a measure unit expressing a very small quantity of energy, so from joules all the way to exajoules. So a tennis ball has about 100 joules, whereas an egg, therefore food, we already have hundreds of kilojoules. While car fuel, as you can see in the image, well, if we think of the amount of fuel burnt by a car to cover 100 kilometers, then we get to megajoules or hundreds of megajoules. And how much energy do we spend to heat up a detached single-family home in a year? Well, here we're talking about gigajoules. And if we consider a town, then we're dealing with almost with exajoules. And finally, if we consider all the energy used around the world, we have several hundreds of exajoules. So as you can see, depending on the phenomenon we're talking about, we move in a very wide range of values. Now, let's go a bit deeper. And in order to do that, the first question we should ask is, what is energy? And this question already poses some problems. And why am I saying this? Well, because we all use this term, and when we do, while speaking with others, we assume that everyone understands us. Just like when others speak, we assume that we understand them perfectly well. We do not ask ourselves what energy is, We just use the term because we have associated an idea to the word, and we make this association because, in fact, this term is within us. We have been hearing it and using it since our childhood. And at the beginning, when we first heard it, we associated it to certain meanings in the contexts where it was used. And since then, and through this process, we have taken and used this term. But nobody has ever given us a definition. Nobody has ever told us, well, energy is this and that. So, a definition. So we have associated it to a certain meaning, but we're not truly able, at least you are not able, to actually give a definition of what is energy. So, in order to try and find an answer, let's look at what has been said over time about this term and its meaning. So, the first researcher who has been credited with finding a definition for energy, and then this depends on the authors. Of course, it's difficult to be certain about this kind of credits, but most authors agree on the fact that the term energy was first used by Aristotle. Of course, he used a Greek term, energia, with the meaning of action, work in progress, and ability to act. And the word is made up of two parts. The first one means inside or in, within, and the second part means work or action. So already, when using this term at the beginning, we wanted to express the idea that energy has this possibility, this ability. Let's then jump ahead in time and see what we find, so what definition the Britannica Encyclopedia gives of energy. And let's begin in 1842. Of course, I did not have the Britannica Encyclopedia's 1842 edition. I found this definition in another text I quoted in the slide. Anyway, in 1842, the definition by the Britannica Encyclopedia was still quite vague. It doesn't really help us to answer the question because it talks about power, virtue, efficacy of something. And moving on to today, on the web, we can find today's definition of the Britannica Encyclopedia. And as you can see, the definition today is energy is the capacity for doing work. It may exist in potential, kinetic, thermal, electrical, chemical, nuclear, and other forms. So a similar definition, maybe just a bit richer, can be found in the Italian Treccani Encyclopedia, which says that energy is the ability that a body or a system of bodies has to do work, both in terms of energy in action and energy potential. So it adds this distinction that is not highlighted in the Britannica Encyclopedia. Well, these two definitions are the ones commonly found on the internet, on many websites and textbooks. It is the prevailing definition of energy. However, I believe this definition is not complete. it doesn't include certain aspects of energy that I will try and explain later that are very important. So we jumped from Aristotle to nowadays, and sure, we can say that attempts have been made to answer that question. But in line with this idea I shared, that this definition we've seen does not include all the meanings of the term, I would like to quote the words of the great physicist Richard Feynman. He was awarded the Nobel Prize for Physics in 1965. And as you can read on the slide, he said, "It is important to realize that in physics today we have no knowledge of what energy is." This is quite a serious statement. Thank goodness it's Feynman who made it. And then he goes on reasoning and some considerations he made earlier and that are not included in this quote. But then he adds, "It is an abstract thing in that it does not tell us the mechanism or the reasons for the various formulas." What does he mean with this sentence? Well, we can calculate energy in its famous various forms, and we can reason on energy and quantify these reasonings, but so far, our knowledge of energy, and therefore our definition, does not allow us to justify those mathematical relations we use. In other words, those mathematical relations stem from other considerations that are not the definition of energy. And I would say this is quite an interesting aspect in order to try and understand what energy is. So what happened between Aristotle and Feynman? Well, in between, several scientists and researchers dealt with the problem, and not everyone tried to give a definition of energy, but they dealt with the physical aspects linked to energy or determined by energy. As you can see in the image, there's a list of names. We have Kepler, Descartes, Bacon, Galileo, Newton, Leibniz, Young, and all the others. This already tells us that between Aristotle to Kepler and Descartes, there was a gap. There was a moment when energy was not so much at the center of attention. Then we have these researchers who dealt with the issue, but didn't give a proper definition. As Feynman says, we do not have a definition of energy. However, as you can see on the blackboard behind Feynman, we have been able to add a number of adjectives to the word energy to identify several forms of energy. So we have kinetic energy, potential energy, electrical energy, gravitational energy, etc. So all these researchers were not able to agree on a single definition of energy, yet their study, their work, brought us to the two pillars of thermodynamics, and the two pillars of our knowledge of the physical world, because these are among the fundamental laws of physics. I'm talking about the first and the second law of thermodynamics. And thermodynamics is the theory that describes and studies all phenomena where energy is a characterizing element. So I have decided to share these considerations on energy without using mathematical formulas. So you can see the first and the second law here, but without either the definition, giving you a definition or the mathematical formula. Yet I would like to convey the message, or at least one of the messages that we can get from the first and the second law. So let's start with the first law, which, as you can see and as you know, stipulates the conservation of energy. What does this mean? Well, the first law allows us to analyze and understand one instant. And I say in slide, let's take a picture. To take a photograph of the situation, and based on that, you make a balance. So we take a picture of a situation, and within that situation, we can calculate all the forms of energy represented there. And we're sure that calculating the forms of energy getting in, those getting out, and all the forms of energy that are kept or released. So they were inside the system, inside that picture, and they are released. So in every instant, when we carry out this type of analysis, the first law guarantees us one thing, which is that so the balance must be the same. So in the end, the figures must add up. Exactly as it happens in a company, so revenues, income, costs, everything needs to be balanced out because energy is conserved. So it's not possible for energy to disappear or to appear. The amount of energy needs to be the same. Then you can understand the analysis potential that the first law gives us. And what happens if the numbers don't add up? That is in second image. It means that I am missing something and I need to go and look for it. It's not that the numbers don't add up because the first law is not respected. The first law must be respected. That is our strength in this analysis. So we need to look for everything that we're not seeing. And this is the message of the first law of thermodynamics. With the second law, a picture is no longer enough. So the second law says that if we want to understand something more, we need to make a movie. We need a succession of moments. This means that time cannot be disregarded. And as you can see, I included an hourglass to represent time going by. And the second law also tells us that the direction of evolution is fixed. So we cannot rewind this movie. Well, among all the fundamental principles of physics, the second law is the only law that is translated into mathematical terms using this equation, so not an equation. And this is very important. It's a message, I believe, we should think about. The second law says that there is a threshold that you must stay below of. So there are limits in what we do. Natural phenomena that we observe, they have limits, an upper limit, I would say. And when we imagine other situations other than physical phenomena, well, thinking that we move in a physical world that is limited is a very important thought, one that we should always take into consideration. Now, to further highlight the importance of the two laws of thermodynamics and this science altogether, I would like to read to you a quote by Einstein, which he wrote in an autobiographical note, and I found it in a science article from 1967 by Klein. Einstein says, "A theory is the more impressive, the greater the simplicity of its premises. The more different are the kinds of things it relates, and the more extended is the area of applicability. Therefore, the deep impression that classical thermodynamics made upon me. It is the only physical theory of universal content which I am convinced that, within the framework of applicability of its basic concepts, will never be overthrown." And this is very meaningful, as it was said by Albert Einstein, who had clearly proven quite good at overthrowing theories. So we've understood that we do not have a clear definition of energy, but this path brings us to thermodynamics. And the knowledge and the analysis potential of thermodynamics enable us to understand phenomena linked to energy and also understand a bit what energy is. I would also like to highlight that all these developments, so this thought elaboration, is quite recent compared to other theories, like mechanics, for example, which was already developed in the 17th century. So thermodynamics is a young theory, and perhaps it's also because of this that we're still reasoning on things and still haven't understood what energy is. So to prove to you that this theory is young, I would like to use the words of great scientists again. And in this case, we start with Maxwell. In his Theory of Heat, published in 1871, that is almost at the end of the 19th century. Well, as you can see, I've highlighted the main points. And basically, in this essay, Maxwell begins by recognizing the contribution of many other scientists that I have already mentioned regarding energy. So this part begins by him saying what is meant by work and what is meant by energy. He says we're focusing on the explanation of what is work and what is energy. He had explained work because, as I was saying, mechanics was consolidated, so there were no doubts on the definition of work. And then he gets to the definition of energy, so he makes an attempt to answer this question we're asking. Then he begins a list of recognitions to scientists, scientists who have preceded him. So he says, thank you, Leibniz, for studying kinetic energy. Well, Maxwell says, Leibniz, you talked about vis viva, but basically that was kinetic energy. Then he thanks Newton for his contribution, etc. And I highlighted all of these passages, but there is no point where he says, well, energy is this and that. Once again, we're trying to give a definition of energy through its various forms, that is potential, kinetic, electrical, etc. And here we see why I say that the thermodynamics theory is young. In the last part, in yellow, Maxwell says something else, something more. He highlights the fact that the first law is still seen in terms of potential and kinetic energy, and the need is felt for more demonstrations. Maxwell states, and I quote, "We cannot even assert that all energy must be potential or kinetic, though we may not be able to conceive any other form. Nevertheless, the principle has been demonstrated by dynamical reasoning to be absolutely true for systems fulfilling certain conditions, and it has been proven by experiment to be true within the limits of error of observation, in cases where the energy takes the form of heat, magnetization, electrification, etc. So that the following statement is one which, if we cannot absolutely affirm its necessary truth, is worthy of being carefully tested and traced into all the conclusions which are implied in it." So he is making certain statements, but he says they still need to be tested. So in 1871, the first law of thermodynamics hadn't been completely accepted yet. Now let's see what Max Planck says. He was a Nobel laureate for physics in 1918, and he wrote an essay on thermodynamics that was published 7 times. So the first edition was published in 1897, the 7th one in 1922. That means after World War I, so exactly 100 years ago. So here too I highlighted the significant parts, and I'm going to read them out to you. He says, I quote, "We shall not attempt to show how this single fact of experience, quite independent of the mechanical view of nature, serves to prove the principle of energy in its generality, mainly for the reason that the validity of the energy principle, this is the first law, is nowadays no longer disputed. It will be different, however, in the case of the second law of thermodynamics, the proof of which at the present stage of the development of our subject cannot be too carefully presented. The general validity of this law is still contested from time to time, and its significance variously interpreted, even by adherents to the principle." So he wrote this the first time in 1897. Maxwell had written in 1874, so it was more than 20 years later. And we can actually say that at that point, the first law was widely accepted by everyone. It was consolidated. But the second was not yet so sure. And even those who supported it gave different interpretations of it. So, and if we take the 7th edition, that was written in 100 years ago. Let's move on to Enrico Fermi, also a Nobel laureate in physics in 1938. In the summer of 1936, he gave some lectures at the Columbia University, which were then published. In his lectures, he confirmed the things I've been saying, so that the thermodynamics theory is quite young, because he says, quote, "Only in comparatively recent times have physicists recognized that heat is a form of energy that can be changed into other forms of energy. Formerly, scientists had thought that heat was some sort of fluid whose total amount was invariable, and had simply interpreted the heating of a body and analogous processes as consisting of the transfer of this fluid from one body to another." End quote. That was the so-called heat fluid theory. Quote, "It is therefore noteworthy that on the basis of this heat fluid theory, Carnot was able, in the year 1824, to arrive at a comparatively clear understanding of the limitations involved in the transformation of heat into work." That is, of essentially what is now called the second law of thermodynamics. Only in 1842, only 18 years later, Mayer discovered the equivalence of heat and mechanical work and made the first announcement of the principle of the conservation of energy, the first law of thermodynamics. So Fermi underlines, first of all, that all of this is recent, and then the fact that the second law was actually announced before the first law, because the equivalence between heat and work was only confirmed afterwards. Therefore, he says it's surprising how Carnot was able to observe the phenomenon and made his observations. And I would like to read out a passage from Carnot's text. So his main work as regards the second law is the title is "The Power of Fire," or "The Power of Fire Machines," depending on the Italian translation of the title. As you can see, this book is not very thick, but of course it's very rich in terms of concepts. It's quite dense. But I would like to point out that without the preface and the conclusions, the text written by Carnot is this. So the text which gave birth to the second law of thermodynamics is this. You see, just a few pages that are very rich in content. And I wanted to read what Carnot wrote regarding the statement by Enrico Fermi. So Carnot says, quote, "The production of power in steam engines is not linked to a consumption of heat fluid." And you see, he mentions the heat fluid, which proves that the first law had not been recognized yet. So not to a consumption of heat fluid, but to its transfer from a colder body to a hotter body. And then, let me jump ahead, and he goes on by saying, "There follows that in order to generate power, producing heat is not sufficient. We also need a cold body, without which heat would be useless. So this part, as Fermi said, this and other parts that maybe I will read later, so this sentence already highlights a very important point on the second law. He says, you do not only need energy, that is a hot body, but to do what you want, which is to transform it into power, you also need to have a cold body. So you need to have a difference, an imbalance. And later on, we will see that the term imbalance will come back. Okay, let's go back to our question after this historical overview and after having highlighted how young this theory is. Let's go back to our question on the definition of energy. At this point, I feel I have to give you a definition because, as I said, I think the first ones I showed you are a bit limited. Of course, I don't want to say that this is the definition. It is one of the possible definitions that might be useful to understand the arguments that will come later. So we can say that energy is a physical quantity associated with the quantity of matter in bodies. So it's associated with mass. But it's also a physical quantity, so it can be one, but also the other. So it's a physical quantity associated with the interaction between bodies. For example, heat, work, electromagnetic waves. But while the physical quantity associated with this mass is always there, I can see it at every moment, provided we can see energy. When I talk about the energy that I define as a physical quantity linked to interaction, well, this energy is there only at the moment of the interaction. So it's only there at that moment when the two bodies interact and there is a transfer or an exchange of energy. Only that moment we can see that energy. So one is there and can last in time. The other is linked to the action being carried out at that moment. So energy is a property of matter that can be transferred from one body to another, and it can move within one body. It is important to point out, though, that the transfer or movement of energy is both cause and effect of all changes in the sensible world. And at the same time, it's demonstration, it's proof that the change has happened. To try and explain this, I can use different words. So when energy does not move, basically there is a balance and bodies do not transform. And this concept of transformation includes the concept of life. So if there is no energy transformation, there is no life. Living beings link their living to the fact that they transform energy. Another point we can make, it's not a definition, but it helps to understand what energy is that in the universe energy is constant, and we've already said this, but it is not homogeneously distributed. So there are points where there is more energy and points where there is less energy. So there are imbalances. And besides sharing a definition of energy like the one I have just given you, I believe it's important also to clarify the terms we use. And why am I saying this? Well, let's think. I've been doing this right now in these past minutes. I've been trying to explain some concepts to you, and I have used terms like producing energy, consuming energy, or the need for energy, using energy, and we can find several other expressions like these ones. We normally use these expressions, which make us think that, or have this idea that we can destroy energy or produce energy. But of course, this goes against what was said by the first law. That is that, as we know, the quantity of energy is always the same. Energy is conserved. So we do not consume energy. We do not produce energy, for sure, and we don't destroy it. So what do we really need? So what are we doing when we say that we're producing energy? Well, if we think about it, we realize that what we do is we transform energy, and we use these transformations. So we do not use energy, but we use its transformation. This concept is always true. For example, also when we talk about renewable energies, well, energy cannot be renewed because energy is always the same. The quantity of energy will never change. It will always be the same. So what am I renewing? Actually, I am renewing the act of the transformation of energy. So with renewables, we transform the energy coming to us from the sun or linked to the action of the sun. Let's think of a solar panel, for example. We transform this energy from the sun, that is electromagnetic waves, into electricity. So the part that is called renewable is not energy, but it's transformation. So we can think that we can renew this transformation for a very long time, because in order to do this in theory, we just need the sun to always be there. And as you know, the sun's life expectancy is guaranteed for a million of years. So we can actually talk about the renewability of the transformation of energy. And I want to highlight once again that the quantity of energy is always the same. So if we focus not so much on energy, but on the term transformation of energy, then we also need to agree on the meaning of energy transformation. So let me specify that energy transformation means both a change in the type of energy. For example, I can transform heat, that is thermal energy, into mechanical energy, or from mechanical energy to electrical energy, or the example I just made with the solar panel. But the transformation can also just be a change in the characteristics of that energy. So I do not change its form or type, but I change its characteristics. For example, the thermal level of that energy or the chemical composition. So again, I'm showing you some images to try and explain better this concept. For example, in the case of fire, the transformation is from the chemical energy included in the wood through a combustion. We get combustion products which have thermal energy. Please consider also that in the process we see in the image that thermal energy goes to the environment. So at the beginning, it would be thermal energy that is at a very high temperature, and then it disperses in the environment, and then it reaches the same temperature of the environment. So the chemical energy in the wood is the same quantity of the thermal energy in the fumes and then in the environment. So the general quantity of energy is the same, but it changed its form from chemical to thermal, and then there was a change in the temperature. Let's think of the great hydroelectric plants. There again, we're transforming potential energy into kinetic energy, then mechanical energy, and then through an alternator in electrical energy. Even our breathing is another continuous transformation of energy. But even the wing stroke of a bird is an energy transformation that starts with all the energy transformations taking place in our bodies, so chemical mechanisms inside our body that stimulate the muscles, and then muscles will move the wings, and wings will create movement that is kinetic energy. In the case of heating, and here it is represented by a radiator, here we have thermal energy at high temperature that is transferred to the environment. So we have a change in the thermal level. There's a transformation because the thermal level changes, but there is no change in the form of energy. Then I decided to mention the classic example of food cooking, because here, well, we can assume that the fuel is methane. We have chemical energy, again a combustion, hot fumes, and so the thermal energy is transferred to the pot and, of course, to its content. And the content doesn't change its form of energy, it only changes its thermal level. So energy is transferred to the content of the pot, and the energy transformation that happens in the content of the pot is a change in temperature. This, of course, unless the water evaporates or other phenomena happen. So energy transformations are the key. Therefore, the question we should ask, after having understood that transformation is the key element of our argument, now the question is, in order for an energy transformation to happen, what is the necessary condition? What needs to be there for a transformation of energy to happen? And the answer is that we need to have an imbalance, a disequilibrium. You will remember Carnot, we just read it. He said that you need to have both a hot source and a cold one. You need to have a difference between the two, otherwise there is no transformation. So, in order for an energy transformation, that means evolution, let's remember that if there is no energy transformation, there is no life, everything stops. So the point is that we need an imbalance or a disequilibrium. However, every time there is a transformation, the initial imbalance decreases. So an imbalance is the necessary condition to make the transformation happen, but the transformation consumes the imbalance. So it's in this sense that we have to really analyze and study the issue. And that is why at the beginning I said that the definitions of the two encyclopedias weren't that complete, because there can be energy inside a body without imbalances around. So it cannot transform anything into work, but that energy is still there. So the point is no longer energy in action versus energy as a potential, because in that case, energy is neither in action nor a potential, yet it's there. So as you can see, the hourglass now has a meaning. The sand inside represents imbalances. So as time goes by and life goes on, we transform energy. But every time we do so, the imbalance is consumed a bit more. So the final scenario is well known. The final scenario is that of a complete balance, because as imbalances get consumed, we will reach a complete balance. So in thermodynamics, the scenario where everything is in equilibrium is a dead state, because if everything was in equilibrium, life would not be possible. Now, first of all, this scenario will not affect future generations. It will affect humankind if humans are able to survive many other events, but it will be a problem when the sun starts burning out. But, as I explained earlier, we still have billions of years ahead. So this scenario where there is no more imbalance, because the main imbalance from which we derive all forms of energy, that is basically the difference between the temperature of the sun and the temperature of the earth. So reaching the dead state is not an issue, but it's a fact that we're heading in that direction. And once again, I say, let's consider the dead state. There, the quantity of energy would still be the same, but it wouldn't be different. But we wouldn't be able to transfer it and transform it. That's one more reason why I find the Britannica Encyclopedia definition incomplete. That energy cannot produce work, yet it exists. Now, consider that all these comments are true both when we transform fossil fuels and when we transform the so-called renewable energies. So even the conversion of electromagnetic waves from the sun into electricity, that is a transformation of energy, and it is also consuming that imbalance. Of course, we focus on renewable energies because we think about CO2 emissions. So, for us, that is the most important aspect, and that is why we're betting on that form of energy. But we shouldn't forget that also in that case, we are heading in this set direction. So, as I am showing in this image, we cannot stop the sand for going down the hourglass. Because if we stop the sand, it means we're no longer transforming energy, and therefore there is no life. So we will keep on making transformations, and sand will keep on going down, imbalances will keep increasing. Of course, what we can think of doing is reducing the speed of the sand falling down in the hourglass. And how can we reduce it? Well, we cannot give up transforming energy altogether, because energy transformation equals life. And we've said that. So it's to be understood if we can reduce the number of energy transformations in order to slow down the system and, let's say, the flow of sand in the hourglass. So to answer this question, we need to exactly understand what energy has represented for human beings. So in the second part of this lesson, we will analyze these aspects. We will see what energy has represented in the history of human beings and what is the link between energy and other human activities.